Module 12.2 video. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 12.2. How can we use the sampling distribution to find an interval of reasonable values for the parameter? In previous modules, we discussed how to collect sample data and how to summarize data. In this module, we'll continue to look at how to take the information contained in a sample to learn about the population. Our goal is to learn how to translate the information contained in a single sample to learn about the parameter. The most simplistic way to do this is using a point estimate. A point estimate is a single value estimate of the parameter we are interested in learning about. It is our best guess. The statistic from the sample can be used as a point estimate. For example, the sample mean x bar is a point estimate for the population mean mu. The sample proportion p hat is a point estimate for the population proportion p. We could also extend this to a difference in means or a difference in proportions. We know due to sampling error that the statistic or point estimate is rarely exactly equal to the parameter, and due to sampling variability, the statistic varies from sample to sample. Instead of using the point estimate, which is a single number, we can use an interval estimate. An interval estimate gives an interval of plausible values for a population parameter and helps us account for sampling variability. We can use a sampling distribution to help us motivate how to construct an interval estimate. Consider the following example. Suppose I have a spinner that is split evenly into two colors, pink and blue, and I want to know out of an infinite number of spins what percentage of the time I would land on blue. I take samples of size 20. I do this by repeatedly spinning the spinner 20 times and calculate the percentage of times I land on blue out of the 20 spins for each sample. Notice this is a special case where I know the value of the parameter. Since the spinner is fair, I know that the population proportion p is equal to 0.5. Notice this is the example from the worksheet that you did in Module 12.1. Here we have a simulated sampling distribution for this example where 100 samples were selected. Our goal is to construct an interval that is likely to cover the parameter. First, notice that since we are working with proportions, we could propose the interval 0 to 1. This interval will always contain the parameter when working with a single proportion, since proportions are restricted to the interval between 0 and 1. The problem with this interval is that it is not very informative. Let's look at the sampling distribution to see if we can construct a better interval. Recall that each dot on the plot represents a statistic. We will start by drawing a vertical line where the parameter is located. Keep in mind that usually the parameter is unknown. Next, notice that 98% of the statistics fall between 0.3 and 0.7. Looking at the plot, we can see that this statistic falls outside, and so does this one. Since there are 100 statistics represented in the plot, 98 fall within the blue box. In other words, 98% fall between 0.3 and 0.7. The furthest any of the statistics in the blue box are away from the parameter is 0.2. Notice the distance from the parameter to here is from 0.5 to 0.7, which is 0.2, or from here to here is also 0.2. For any of the statistics in the blue box, we could create an interval centered at the statistic, or in other words, centered at any of the dots in the blue box, with length 0.2 on either side, and the interval would cover the parameter. For example, this interval shown is centered at p hat equal to 0.65. We could move the center, this piece right here, to any of the statistics inside the blue box, and the green line would still cross our parameter, represented by the orange vertical line. What if the green interval is centered outside of the box? Notice this interval is centered at p hat equal to 0.75. The statistic is outside of the blue box, and the interval does not cover the parameter. If the center of the green line moves outside of the box, the interval no longer covers the parameter. This tells us if we use the interval, the statistic, plus or minus 0.2, 98% of the resulting intervals will cover the parameter. Notice that for all of the statistics in the blue box, we get a more informative interval than the interval 0 to 1. The cost of the more informative interval is that for some values of the statistic, the resulting interval will not cover the parameter. How can we find an interval of reasonable values for the parameter if we only take one sample? Notice that creating a sampling distribution required us to take many samples from the population. In the real world, we only get to select one sample from the population to help us estimate the parameter. One common form of an interval estimate is known as a confidence interval. Confidence intervals are given by the statistic plus or minus the margin of error, where the margin of error, or MOE, reflects the precision of the sample statistic as a point estimate for the parameter. The margin of error is constructed by taking into account the standard error and the percentage of intervals that would cover the parameter based on the behavior of the sampling distribution. Definition: a confidence interval for a parameter is an interval computed from sample data by a method that will capture the parameter for a specified proportion of all samples. The success rate, proportion of all samples whose intervals contain the parameter, is known as the confidence level. A p% confidence interval will contain the true parameter for p% of all samples, where p% can be any percentage from 0 to 100%. In another picture, the black vertical line represents the parameter. The parameter is a fixed number. It does not change from sample to sample. Each small circle represents a statistic from a random sample. The statistics are random. In other words, they depend on the sample. So looking at our diagram here, again, the black vertical line represents the true value of our parameter. Notice that each of the dots represent a statistic. Two things to notice here. Not all of the statistics fall directly on the parameter. This is the sampling error we spoke about earlier. Also notice that the statistics vary from sample to sample. This is the sampling variability that we referred to earlier as well. Each horizontal line represents a confidence interval centered at the statistic. The interval is random because it depends on the statistic. If the intervals are 95% confidence intervals, then 95% of the confidence intervals will cover the parameter. Notice there are 95 green intervals which cover the parameter and 5 red which do not. Using the formula, the statistic plus or minus the margin of error requires that we know something about the behavior of the sampling distribution. In other words, we need to ensure that the sample size requirement of the central limit theorem is satisfied. The only difference in checking the sample size requirements is we need to replace p with p hat in the sample size requirements for a single proportion and in a difference of proportions. Example: in 2018, a random sample of 155 UK students found that the average number of text messages sent or received per student a day is 41.5 messages, with a margin of error for a 95% confidence interval of 12.2. Confirm that the sample size requirement for the central limit theorem is met and give a 95% confidence interval for the average number of text messages sent or received per day for UK students. First, notice that we are working with a single mean. To satisfy the sample size requirements for the central limit theorem, we need at least 30 people in the sample. There were 155 people, so the sample size requirement is met. Further, another thing that we need to make sure to note is that in order for the inferential procedures to be valid, we need a random sample. Notice in the example we do have a random sample. The statistic here is x bar is equal to 41.4. Also, we have a margin of error equal to 12.2. The calculation for the interval is as follows. The statistic plus or minus the margin of error gives us the interval 29.2 to 53.6. Confidence intervals are important because they give us a range of plausible values for the parameter. Suppose that a 95% confidence interval for a population proportion is 0.7 to 0.9. First, what statistic was observed in this sample? Based on the formula for a confidence interval, we know that the statistic is located at the center of the interval. The center of this interval is located at 0.8, so this tells us that the sample proportion was equal to 0.8. Is 0.85 a plausible value for the parameter? Notice that 0.85 is plausible because it's located inside of the interval. Is 0.2 a plausible value for the parameter? No, because 0.2 is not located in the interval. How do we interpret a confidence interval, and what does it mean to be confident? Confidence intervals have a specific interpretation. The interpretation of confidence intervals must include three things: the level of confidence, a reference to the parameter of interest, and the calculated interval. An example of the interpretation of a p% confidence interval is the following. We are p% confident that the parameter of interest is located in the interval a to b. P% of all samples yield intervals that contain the true parameter, so we say that we are p% confident that one interval contains the truth. The word confident is very important and holds special meaning. To be p% confident means out of a long list of confidence intervals, p% of the intervals will cover the parameter. Looking at our previous example, we are 95% confident that the average number of text messages sent or received by UK students per student per day is between 29.2 and 53.6 text. Let's identify the three different pieces of the interpretation. Notice at the start we say we are 95% confident. This piece is important because it acknowledges our error. In other words, it acknowledges that we have made a smaller interval than 100%, and there's always the possibility that the interval that we calculated does not cover the parameter. We reference the parameter of interest, which in this case is the average number of text messages sent or received by UK students per day. In other words, this is the parameter that we're trying to estimate. And then finally, we give the interval that we found. There are many common misinterpretations of confidence intervals. Let's look at some. Misinterpretation 1. A 95% confidence interval contains 95% of the data in the population. Keep in mind that confidence intervals help us estimate the location of the parameter, not data. The interpretation should always refer to the location of the parameter we are interested in learning about. Misinterpretation 2. I am 95% sure that the mean of a sample will fall within a 95% confidence interval for the mean. Again, confidence intervals help us estimate the location of the parameter, not the statistic. We know that the statistic will always be inside of the interval. The interpretation should always refer to the location of the parameter and never the statistic. Misinterpretation 3. The probability that the population parameter is in this particular 95% confidence interval is 0.95. We have to keep in mind that the parameter is a fixed unknown number. We can only talk about the probability of random events. Since the parameter is fixed, we never attach a probability to it. Additionally, once the confidence interval is calculated, it is no longer random. How do the sample size and level of confidence affect the margin of error? Recall that the margin of error reflects the precision of the sample statistic as a point estimate for the parameter. The margin of error is constructed by taking into account the standard error and the percentage of intervals that will cover the parameter based on the behavior of the sampling distribution. This tells us that changing the sample size or the confidence level will change the margin of error. What happens to the margin of error as we change the sample size? The larger the sample size, the more precise the statistic is as a point estimate. Larger sample sizes will produce smaller margins of error. Since the margin of error is smaller, this will produce a narrower confidence interval. The smaller the sample size, the less precise the statistic is as a point estimate. Smaller sample sizes will produce larger margins of error. Since the margin of error is larger, this will produce a wider confidence interval. What happens to the margin of error as we change the level of confidence? Recall that the confidence level is the proportion of all samples whose intervals will contain the parameter. To change the proportion of all samples whose interval contain the parameter, we need to widen or shorten the confidence intervals. The higher the confidence level, the larger the margin of error. Since the margin of error is larger, this will produce a wider confidence interval. The lower the confidence level, the smaller the margin of error. Since the margin of error is smaller, this will produce a narrower confidence interval. Where will you see confidence intervals in everyday life? Take a moment and pause the video and read the excerpt taken from a news article provided in the script. You've probably seen articles similar to this one in the past. Notice that the article claims majority of Americans back stricter gun laws. Let's apply what we know about confidence intervals. First, notice that the statistic the headline references is that 54% support stricter gun laws. Using the notation from the course, we have the following. P hat is equal to 0.54. The article also states that the margin of error is equal to plus or minus 3 percentage points. This informs us that a range of reasonable values for the proportion of all Americans who support gun control can be found by using our formula for a confidence interval, the statistic plus or minus the margin of error. Notice this gives us an interval from 0.51 to 0.57. Notice that the interval lies entirely above 50%. Therefore, the claim made by the headline is reasonable. What are some common confidence intervals that you may see in research? This section is optional reading and provided as a reference for later use. Located in these pieces or these parts of the script are several links to different applications and confidence intervals with links or where you can read about these in the optional text. This ends the Chapter 12.2 notes.